Alba?
Yeah, you're good to go. Thank you.
Can we start?
Yeah.
Okay.
Go ahead. Thank you.
Okay. So today's speaker is Emilio Elizalde. He's a professor at Honorem here at the ICE-CSIC. And today he will talk about who was the first to discover that our universe expands and that it had a beginning. So, floor is yours.
Thank you. Well, this will be for many an obvious question, but well, I will start before with some facts that I have seen recently. One was that my 40-year-old grandson the other day was speaking that the universe, he said, the universe expands. I was surprised by this fact. No, the universe expands. So, okay, this is just a fact. And then he said, and accelerates. Second, I have read in different places now that it was not Hubble, it was Lemaître, the one who discovered all these things that the universe expanded was Lemaître, and he did a poor job. Well, I will talk about that. And then again, we have this mantra that is unbeatable, that the Big Bang is a huge explosion. So, you know, all the world is convinced about that, and it's impossible to fight against this idea. It's just impossible. I have found it impossible. You know, it's even if you say, what exploded? What exploded? Big Bang exploded, you know, it was concentrated and exploded. This I found impossible to fight, just to say that. On March 14, so 1 month ago, remembering Stephen Hawking 6 years after his death, I wrote up an article for The Conversation, Las 4 Preguntas Fundamentales de Stephen Hawking, that has been read by many people, translated to different languages. It was in National Geographic and in BBC, and it was quite successful. And then, as an answer to my, of course, in this article, it's a very short thing, yeah, because in The Conversation there are very short articles. This is the main problem, that you should condense everything there. And that, of course, that talking about Hawking's theorems, singularity theorems, and that the first discovery of Hawking was that the universe, the space and time, well, Hawking and Penrose, space and time have an origin. And then someone disagreed with that. How could Hawking discover that the universe has an origin when this was discovered some decades before by Lemaître, one of those defenders of Lemaître? This was by Lemaître. And now, yeah, and I thought that it has sense to ask who was the first to discover the universe expansion. This is the question. It seems simple, it's not so simple. Who was the first? Who was the first? And that the universe had a beginning. Well, to start answering, first, we should concentrate on the word. What does it mean, discover? As always. What does it mean, discover? What does this mean? And in order to answer what does this mean, we have to settle the playing ground, the playing field, to choose the deck of cards with which we are going to play. With which deck of cards are we going to play? What are the rules of this play? Simplifying, there are two possibilities. One is the deck of cards of speculations, intuition, guesses, half proofs. And the other one is another deck of cards, that of rigor, theorems, precise experiments, and observation. Of course, you here belong to the second one. You belong to the second one. And so here, this is where, you know, it's not so fair to this thing. But yes, it is. Yeah, this is very important for the problem we are trying here, the question we are trying here to answer. let's contrast Hubble versus Lemaître. Until recently, Hubble was the great discoverer. It still is for many. It still, Hubble did everything, all the shop. I was once, I told this some time ago here, I remember, that I was in Tenerife in one of these meetings, these famous meetings, Star Mass, with Hawking surrounded by 15 Nobel Prize winners. Imagine, So it's like this meeting that is in Lindau, the meeting of the Nobel Prizes. This one is it was comparable. 15 Nobel Prize winners were there, and Hawking. This was really something. This was really something. And it was for young people. It attracted lots of young people and their parents. They went there to learn about science, about cosmology, and music also. Music was playing. Those were really happenings. Really important happenings. And in one of those happenings, one of these Nobel Prize winners said, to an enormous audience, 1,000 people there, 1,000 people there. And he said that Hubble had calculated distances to distant objects, velocities, then they used the Hubble law, this proportionality law, and then said that the universe is expanding. But this was said in this way by one Nobel Prize winner, maybe simplifying, what was the idea? Now, Europe in many different places, I have read, mainly there is a community of supporters, French-speaking, mainly, that no. Well, of course, Hubble law is now Hubble-Lemaître law. Of course, he did something, yes, Lemaître, but not he did something. Lemaître not just did something, he did everything. Because Lemaître obtained Hubble law 2 years before Hubble, obtained Hubble law, and also obtained Friedmann's equation, interpreted Friedmann's equation in relation with the data, with the astronomical data, with the Hubble law, and she said that the universe is expanding. And he was really the first. Even Friedmann has lost relevance because they say no, Lemaître obtained Friedmann's law independently of Friedmann, and Friedmann just obtained the solution. But Lemaître matched the solution with astronomical data and connected this and said that the universe was expanding. So it was Lemaître who did the whole thing. So let's shed some light on this conundrum. Now, Edwin Hubble. Common law is that Hubble obtained everything, and concluded that our universe expands. Actually, Hubble obtained only distances. Redshifts were obtained by Hugh Mason in the second paper in 1931. In the second paper, they added some redshifts with Hugh Mason and so on. But essentially, in the first paper, he only obtained distances. So the redshift table was of Schleifer that I have defended in other talks here. And the law he obtained 2 years after Lemaître, because Lemaître was first to obtain the same law because he had the same data, because Hubble had passed him his redshift, his distance data, and Schleifer had passed to Lemaître his redshift data, velocities. So 2 years after Lemaître, and Hubble never believed that the universe was expanding. Never believed. And this was not because he didn't like to believe that. No, he had strong reasons. He was a true scientist. This is the point. Hubble was a true scientist. A true scientist. And And with his data, with the Hubble constant that he calculated, essentially 500, yeah, compared with 70 now, yeah, the universe in this model of Lemaître that he said, well, no, going back, the universe expands and you go back. The universe was 2 billion years old, 2 billion years old. When geologists have found in the earth rocks that are 5 billion years old. So it was impossible that these models, that these models were true. And what was the conclusion? What was the conclusion? The conclusion was that these redshifts were only apparent velocities, because the redshifts were essentially they could have some component of the velocities. They could have, but the essential component was the entire light hypothesis, so that light in his way to us lost energy, yeah, by interaction with the, by interaction with the the medium there, no? So the tired light hypothesis, the interstellar and intergalactical medium lost energy. This hypothesis has been used in many places, in many occasions. Also now to understand the acceleration of the universe, it has been invoked sometimes, that it may have a contribution. And this was what many astronomers, almost all of the astronomers, thought at the time. So, and Hubble was among them. Even he said exactly that. I have the best, this is what Hubble said, I have the best telescope in the world in Mount Wilson. And I look and see, and I calculate, and see that, the universe with the constant that he reduced, with the constant, it can be only 2 billion years old. So it's impossible that this can be true. So this redshift must be something, not just these velocities, cannot be these velocities. There must be another explanation, and this tired light explanation was the most common for all astronomers at that time. So this was the reason. He was a true scientist. It's not just that you fit velocities, distances, and then deduce that the universe expands. Yeah. Yes, it could be, but let's look at everything. No, this on the side of Hubble. Yeah, so Hubble, in my view, was a true scientist. Yeah, playing with deck of cards. Number 2. Georges Lemaître, stand supporters assure now that he did everything. He obtained Friedmann's solution independently from Friedmann. Yeah? He obtained Hubble's law. He proved that the universe expands and has an origin. But actually, yeah, he borrowed all data. He didn't calculate any single data. He was not an astronomer. Yeah? He went to visit Lemaître, and he went to visit Hubble, and they passed him the tables. And so with these tables, he obtained Hubble's law with a constant that was even worse than Hubble, yeah, because Hubble had a few additional data, and in this case was 600 something, yeah, 600 something. So his data were even worse than those of Hubble. But he had no doubt. He had no doubt. In my view, he just guessed, or if you want, half proved that the universe expands. Yeah. No, and also the true story goes further, because these supporters, they say that even Friedmann is not so important, because of course he was first to obtain the solution. Friedmann was first. Yeah, there is no doubt. He was 3 or 4 years first to obtain the solution. But Friedmann just obtained the solution and nothing else. Yeah, and Lemaître, no. Lemaître went to compare the solution he obtained with this data. The first thing is that Lemaître didn't obtain Friedmann's solution, the one that is now known as Friedmann's solution. He obtained one of the family of Friedmann solutions that Friedmann had obtained, one, and it was the wrong one. It was one with a logarithmic contribution, so that the universe didn't have an origin in his paper in 1927, in his French paper in the Belgian journal in 1927. So it was not Friedmann's solution, it was one of Friedmann's solutions and wrong. Wrong solution. This is what Lemaître obtained. Well, the Russian, the Russian cosmologists, they wonder how Lemaître did not know about Friedmann's solution. How he would not know? Because it was in a most famous review, ICE-CSIC, and they conclude that the only explanation was that Lemaître did not know German. He could not read German, and he was not aware. And of course, Lemaître confessed that he did not know it. Yeah, he had not seen it. And even he said that it was my fault. I should have known this, but I didn't know. Yeah, but he obtained one that was not the right one. And it was later in 1929, when Hubble published his paper and Lemaître's paper was translated to English by Eddington. Yeah, because having seen Hubble's paper, Lemaître went to Eddington, saying to him, I sent you already my results before. He sent him his 1927 paper to Eddington before. You see, I had sent you this paper, and you didn't pay attention. And now Hubble, they just deduce the same. Yeah, and this is what Lemaître told Eddington. And then Eddington decided to translate Lemaître's paper to English. There was this controversy that the part where Hubble's law appears was not translated, but now it's clear that this was due to Lemaître, that didn't like to translate this part. It was wrong. Of course, Lemaître never claimed priority of this discovery. Never claimed any priority of this discovery. Lemaître himself, because he was very conscious that he had borrowed things from here, from there, and so. Yeah. And it was Eddington and Einstein before, in 1927, Einstein told him already that there was a Friedmann solution, that his solution had been obtained by Friedmann before. And Eddington told Lemaître that the preferred Friedmann solution, was not the one that Lemaître had recalculated, that had reobtained. It was not this one, but the preferred Friedmann solution was the other one with an origin. This told Eddington to Lemaître in 1929, when translating the paper. And then this opened Lemaître's eyes, because then, with Friedmann's solution that he did not reobtain, it was told by Eddington, and before it had been told by Einstein that there was this Friedmann solution. With the Friedmann solution, then he wrote the paper in Nature, saying that the universe had an origin going back in time. With Friedmann, with the real Friedmann solution, it had an origin. But you must know the whole history, because as I say, these stump supporters say no, that Lemaître obtained Friedmann solution in every. No. Oh, they obtained something, and this was completed in this way. So there was this intervention, and in this Nature paper, the solution that he puts there is the real Friedmann solution, but now knowing that this solution existed and was the preferred one, because Eddington had told him. So this is the whole history. You know, there are some goes and comes. Yeah? And so we have to give everybody his part, but realistically. Yeah? For me, Lemaître was playing with deck of cards number 1 because his data were not better than Hubble's. His data were not better than Hubble's. But Lemaître was not worried about this thing that the universe would be only 2 billion years old. He was not worried with this. Because when you play with these cards, this is for free, you know. You can speculate, you can make your intuition. Of course, this intuition was genius, because later he was right, because this problem that they had with the age of the universe was all due to Hubble's constant, and it was all due to the calculation of distances, the calculation of distances that had enormous errors, calculation of distances, not so the calculation of redshifts that are much more accurate because it was much more precise. But the calculation of distances is extremely difficult, very difficult. And as it is today are still with Hubble constant, the problems that we have. So now let's put people into 2 playing fields. In playing field number 1, we have Lemaître. We have to add Friedmann, because they say Friedmann just calculated a solution. Not only got the solution. Friedmann wrote that it could be that these solutions that I have obtained, but the particular one that he liked most was the one with an origin. It could be that this solution corresponds to our universe. Could be. This he wrote. Of course, he had no proof. He had no contract with astronomical data. No. But he said it could be, and this was his hope. So he had this intuition. This possibility at level 1. And then if you go back at this level 1 of intuition, of guesses, and so we can go to the Rig Veda, Hiranyakarpa, the golden egg appears there, the golden egg as the origin of the universe through a big explosion. This is the Hindu. Okay, is going maybe too far back, too far back. But intuitions we can have. Now proofs. Well, Hubble could not accept the expansion of the universe because it didn't match. It didn't match with observational results. It didn't match with the value he obtained for the constant. But there were these enormous errors that from 500 to 70. There is almost an order of magnitude. And so that was why he didn't believe it. He also didn't understand the theory. And he confessed this. He was humble and confessed to the sitter, in letters to the sitter, that he was unable to understand the mathematical models, that the space could expand. This was a very difficult concept. Well, we have to put here Einstein, Eddington, Hoyle, Hawking, Penrose, and now I will talk a bit of that. So, in this sense, if we go to proofs, to real proofs, we should go to the singularity theorems. Singularity theorems were studied by the Landau group in Moscow, Belensky, Lipschitz, and Kalashnikov, 1963. And they at first were much surprised about Penrose theorem. because he couldn't believe that, that no additional assumption was put there. Yeah, because first the theorems were done for our universe, so imposing homogeneity and isotropy, the cosmological principle. Yeah? And for this, they derived some theorems and so, but Penrose and then with Hawking, they derived these theorems without any further hypothesis. So just an hyperbolic space-time, Einstein's equation, of course, general relativity, Einstein's equations, with the strong energy condition, and the additional and important hypothesis of the trap surface. That the trap surface is formed when we go back in time to the origin of the universe, and we go so forward in time to the interior of a black hole. Yeah, the other case. Yeah, this trap surface hypothesis. And with that, you obtain the theorem that all temporal geodesics to the past are incomplete. There is an origin of space and time. This is rigorous within this hypothesis. Within this hypothesis. Well, and the same for the black holes. Yeah. Well, the fact that a singularity appears already, these people, Hawking and Penrose, yeah, they realize the obvious thing, that the singularity appears in a region of a space that is not covered by general relativity. Einstein's equations, but Einstein's equations are not valid when you go to these small distances. They are not valid anymore. Yeah. So you need quantum gravity. So this cannot be the last word, these theorems. Well, in any case, there is a escape route to the theorems. Yeah. As some of you, at least some of you, will know that Jose Maria Martín Senovilla, this theorem when he was at the University of Barcelona, as we were there at the time, in the campus of the University of Barcelona, and he obtained this astonishing result. The result that he could get around the singularity theorems by because all theorems have some hypotheses. They can be minimal. Yeah, the conditions can be minimalistic. Very general, very minimal. But you can escape the condition. There is another result here. For piecewise Lorentzian manifolds, you can escape the theorems, but in some ways, of course, any theorem, yeah, you can escape. And then there is a more serious thing, that the theorems of the singularity theorems had to be modified because they didn't put into them because of the role that can be played by inflation and quantum corrections. Yeah, and then first there was this result by Borde and Vilenkin in 1994 that proved an extended theorem for inflationary space-times. They proved the same result. For a while in the 80s, it was attempted to construct models that would be past eternal. Yeah? With inflation, they thought, no, we are escaping. Yeah? But it was impossible. It was impossible until this theorem came. Yeah? It was an important result that for inflationary space-time, they are also past geometrically incomplete. So we recover the result of Penrose theorem. And then Borde, Wood, in Vilenkin added some quantum effects. If quantum effects could be stored, yeah, could also eliminate the theorem. Now you have to introduce some additional things, yeah, because the weak energy condition is violated, and you have to put a condition of average expansion. You have to introduce here some additional conditions. Yeah, but in any case, you can say, and this is the state of the art. This theorem, Borde, Wood, and Vilenkin, is already over 20 years old, but is the state of the art of the singularity theorems. Now, when people, of course, this has implications, because that the universe has an origin for people that believe they're creationists, and and for many people, Jesuits, for instance, Jesuits, which are priests, but with a strong humanistic formation and even scientific, yeah. And they have asked me sometimes to go there to explain this theorem, because now this is the theorem, this is the singularity theorems, that even if you put inflation, even if you put quantum corrections, still, our universe has an origin, yeah, and so is important. There is this singularity, yeah, but this singularities, I have this paper. I have this paper that I recommend to you. A singularity, a mathematical singularity, which those are mathematical singularities of the mathematical equation. Always means that the mathematics that you are using to describe the physics, your physical theory, are not the right ones. You should look for something else. This is what a singularity means always. Yeah, that the mathematics show every theoretical, every physical theory, yeah, is valid in some domain. Not everywhere. For instance, if you go to general relativity, and if you go and try to describe an atom, we go with Einstein's equation and try to describe an atom with Einstein's equation. We will fail. Because in this domain, Einstein's equations are not valid. Yeah? So how can we pretend to describe not just an atom, but the Planck scale with these equations? Of course, they are not valid. Simply they are not valid. And the singularities that we obtain in these cases just reflect this fact, yeah, that the mathematical equations that you use are not valid in this region where the singularity appears. They are not valid simply. But this has happened many, many times. And this is what I describe in this paper. Yeah, in the history, how many times has this happened? Already when in the classical physics, you try to describe, in electrodynamics, you try to describe a particle is singular. All particles are singularities. All particles, when you try to describe an electron, what's a singularity? Of course, a singularity. It has zero radius, yeah, and has some mass. Of course, those are singularities. So those are approximations. And then they are solved. This is my specialty. I have been dealing with infinities, with these singularities for part of my life. The singularities. And so I know what I am talking about. And here I explain how in the history it has been resolved. Most typically the singularities in quantum field theories, when they try to construct quantum field theory, quantum electrodynamics, to start with quantum electrodynamics, you obtain infinities everywhere, infinity here, infinity there, infinity there, and they have to give sense to these infinities, and they could give sense to these infinities through the regularization and renormalization processes, So this is the thing. Yeah. So these singularities only mean that, well, new physics is needed. New physics is needed. New physics in the sense that, a new description. A new description. So, it has no sense to take singularities as final thing. A singularity is just a warning. It's just a warning that you have to modify, your theory. You have to modify your theory. One has to say that Hawking, for instance, was very sensible about that, and also Penrose in his talks is very sensible about that, that these theorems, that you needed to go beyond. You need to go beyond to quantize gravity, yeah, or use loop quantum gravity, or the like, yeah, or superstring, yeah, superstring theories, they have their problems. Okay. Well, and more or less, I don't know, but I think that more or less I could finish here. Yeah, I could finish here if you have some general questions, because it's what more or less I wanted to say. Yeah. Okay.
Okay, so thanks. And questions?
When you explained the story about Eddington and Lemaître, I got a bit confused. So who wrote in the end the Nature paper, Eddington or Lemaître? You mentioned that they translated the Friedmann paper.
No, Lemaître's paper.
Oh, Lemaître's paper. So, but then this Nature paper, where you say that they select
This is Lemaître.
So this is Lemaître in Nature.
Yeah, let me explain a bit about that. Yeah, so Lemaître, when he started, well, Lemaître was already a doctor in Belgium, and then he went. His first visit outside was to visit Eddington, and Eddington, it seems that he already realized that he was not really, yes, that Lemaître was looking for a model for the universe. Yeah, he wanted to construct a model for the universe. And Eddington told him about the Sitter solutions and other solutions, but Lemaître didn't obtain new results, and he decided he was not very satisfied by his first visit to Eddington. And then he went to the United States, in a second visit, paid by Belgium. Somebody asked me, it's impossible that Lemaître could visit, and went to the United States, did a PhD thesis at MIT, and visited different people, not only Hubble and Schleifer, but also Millikan and other, big people, yeah, the great people there, and he looked for a model for the universe and so on. And it was at MIT where he obtained this Friedmann solution, yeah, with the logarithmic term, yeah, one Friedmann solution he obtained in his PhD thesis. And then when he came back, he wrote his 1927 paper, this paper where he has this Hubble law in French, and everything. And he sent this paper to Eddington, but he paid no attention to this paper. He paid no attention. And then it was in 1929 when Hubble's paper appeared that Lemaître reminded Eddington that he had sent him his paper in 1927. Well, also in 1927 is when Lemaître spoke to Einstein, yeah, in the Solvay conference in Brussels in 1927. And he told him that about his results and his paper, and Einstein told him that this thing that the universe was expanding and this solution was obtained before by Friedmann. He told him, and that there was nothing wrong with the mathematics, but the physical, this thing that the universe was expanding, this was rubbish. Yeah? This is what Einstein told him. This is everybody knows. And then in 1929, when Hubble's paper appeared, then Lemaître reminded Eddington that I had sent you my paper where all this was already there. Yeah? And Eddington decided to translate, yeah, and it seems that it was he himself who translated this paper, 1927, into English in order to be known. And Eddington wrote himself something in praising the results of Lemaître, that that he had this idea and this solution and so on. And Eddington also told him about the other Friedmann solution, the Friedmann solution, that was preferred. I don't know exactly the words and so, but that told him about this Friedmann solution. And then in subsequent calculations, Lemaître used the Friedmann solution in the Nature paper, because in the other, the universe had no origin. Then he used, but it's not true what the French said now. That no need of Friedmann. No need of Friedmann. There's all this. So Lemaître obtained a solution, but it turned to be not the good one. Not the good one. This is not, this you don't find it in many places. Copy things from one to the other and don't go to the roots. For how things happen.
I have this question because lately some of my colleagues are reviewing my paper, and I use Hubble law, and they have corrected me, like including Hubble Lemaître law.
Sure.
What do you suggest that we should do?
I don't know. This is now the official name, for the International Astronomical Union. There was a vote. There were people voting there. And they decided, because of course Lemaître has his merits, of course. It's in some of my previous talks, maybe I was praising Lemaître so much because when everybody was talking about Hubble, you should defend Lemaître. But now that the balance has gone to Lemaître, too much, because it's the pendulum law that goes from here to the other extreme. It's always like that. And now they say, no, Lemaître did. Even Friedmann, no, I have read this. Even Friedmann, no, because what Friedmann? Lemaître obtained it independently, and then, okay,
But that is just a competition between France and the United States. It was discussed in the IEEE meeting in Vienna, but I don't know what happens after that. So, Hubble the next law, but in the discussion.
I think that many people don't pay attention, but some they pay. You should put it. No, because this is the eponomy law that no discovery. There is. I explained this in another occasion. That no discovery bears the name of the real discovery. This is the law. This is the law. There are exceptions. So there are some exceptions to the rule, but the general rule is that. And in my view, once a tech has been attached to a discovery, but you should take it as you put it a name. It does not mean that this name did everything. Just you put this name. It's very difficult to fight against this. And in my opinion, one should take it in this way. Just a name. This has a name. This has a name. You put here a name, and then okay, you name it in this way. But this doesn't mean at all. Some pretend that this guy did everything. Sometimes he did nothing. Sometimes he did only some part. Yes.
I have a very basic question, maybe tangentially related to your talk, which is, well, you were talking about time, right? And in general relativity, there was always this question of which time are we talking about? So I've read about the notion of a global time, which is the time that we usually talk about, right? When we talk about time in an topic in the universe. When we talk about time, we're referring to this notion of a fundamental observer And that's the time that we call. I've never understood very well what's the argument of this global time. I don't know of any parts. Since we were talking about, well, time, space-time ends, no? I was thinking about, well, which time?
Was the time, you know, here is you know, here this is related with general relativity. You know, you have your physics, but then you have your model. You have your mathematical model. The mathematical model is this is general relativity, and then of course, depending on which relativity you use, if you use the standard general relativity, which we are using in these theorems, everything is related with this theory, is within this theory. Of course, if you change some, you know, yes, yeah, now they are working ways to change and improve and modify general relativity, and different ways you can obtain different things. And so, yeah, now, yeah, in these interpretations that now it seems that the universe was double so old that they say, yeah, this is playing with, you know, it's a bit cheating, so to say, you know. This is what I put at the beginning. You should establish your playing table here, yeah, and the playing rules, and then you say according to these rules. Yeah, and the rules of all these theorems is just GR. Yeah, is GR. You take GR, and you obtain these theorems, yeah, with the geodesics, and so this is rigorous. This is mathematically very, very rigorous. But as I said, every theorem has some hypothesis that you put there. If you change a bit of one, then you obtain a different result. Yeah, and of course, yeah, but are rigorous, rigorous in a sense. No, that you can put your step there, and you are in your theory. Yeah.
I think that what is necessary is to take into account the context. 100 years ago,
Yeah.
Many people don't believe about the general relativity.
Yes.
They
Yes.
were not convinced.
Yes.
Usually, what is necessary is to open the way, open the path. And there is a rule that the pioneer opens the path and the second obtains the faith.
Yes.
Typical rule.
Yes. Yes, this is true. This is true. And this is one example that can be attributed to Schleifer, to Vesto Schleifer and Hubble. Yeah, that Vesto Schleifer was the first, yeah, everybody recognizes it. He was the first to see that this static universe, you know, something was there, because he obtained these redshifts, enormous redshifts for almost all objects. And there were blue shifts, the ones that were approaching us, but the majority, from 24, there were only 3 or 4 blue shifts, and the rest were red shifts. Yeah? And then it was just looking at that, interpreting them at receding velocities. It was very difficult to explain that the universe was static. How could you compensate this? Yeah. So, and this is what Schleifer said, that he has been diminished very much, no? And Hubble was in this talk. Yeah, Hubble was present when Schleifer gave this talk to the American Astronomical Union. Yeah, and in 1914.
Sorry, but the problem is how this pioneering idea pervades the scientific community. This is what is hard.
Yes.
To abandon the.
Yes. No, but in a way, this hypothesis of the tired light hypothesis was very reasonable. It has been invoked many times. It has been repeated many times. We think that, of course, the interstellar medium will play some role, but then you finally see that the role is very little, no? That it's not important. In the different occasions, yeah, normally the role is not important. But yeah, and there was this discrepancy. Right? Just Lemaître didn't think about this discrepancy. He said, you know, you take the yeah, no. Yeah. So you see the the straight line and you get immediately convinced that the universe expands. Yeah. Also, there is the different interpretation that the universe expands, because it could be the objects that go away, not the universe, the frame, the objects. That was another interpretation. Yeah, it was not so immediate. So for me, it's very surprising that my 4-year-old grandson say this in this way. So, as I said, this is a mantra. And you say, oh, the universe expands. The universe expands. Of course, the universe expands and you're happy. Okay.
Maybe I think it's important to realize that this is one thing who did the equations of the measurements first, but the fact that to establish that the universe is expanding, this is very recent, because you know that until probably Kobe found
Oh, yes. Oh, yes.
Kobe found the temperature and the anisotropies. So I think there were still many competing theories and many people defending them in a strong way. Right?
This is true. No. The fact, no, but there was the other version that really these galaxies were escaping, no, that it was not the framework. It was the galaxies that were escaping, and this lasted for many decades. And even many people didn't have problems with that. Even Einstein was the first, it seems now that Einstein was the first to try to rescue the stationary universe, even with Hubble's law. And then came Hoyle and the others. But Einstein had a paper, a draft. They found in his desk. A draft they found in his desk. Well, how can you compensate? How, if objects go away, how can you compensate and obtain a static universe? Creating matter creation. The steady state theory, but Einstein was first in that, but it was a draft and he was not convinced. And he tried to obtain this matter creation through the cosmological constant, but he did not succeed. While the others put there some creation and some creation fields, so more in the way of modern quantum field theories. It was not right, a well-defined theory. It was just an idea, but with a creation field, you could create matter in the interior of some galaxies. You could create matter in order to compensate the matter that is going away. Yeah, in this interpretation, that avoided the universe expansion. It was universe expansion, but in a different way. It was universe, of course, the universe expansion because things were going away, expanded in the way that they were going away, but not the expansion of the frame as we understand it. Yeah.
Okay, so let's thank Emilio again.